Good evening, my YouTube viewers. It is Crystal here, and I'm here this evening to give you another code review. This is going to be on Cackle's Playground Series, Season 4, Episode 1, and I'm going to use Jack's logistic regression model. The problem statement is to identify the probability that a customer will churn. And basically, when a customer churns, that means that they're going to go to another supplier of some sort. So obviously, you don't want the customer to churn, but you're going to predict whether you believe a customer is going to churn or not. So if a customer churns or not, it's going to be 0 if he doesn't churn or 1 if he does churn. But in this particular exercise, you're going to predict on the probability that the customer is going to churn. And in the previous, if you've looked at my previous videos, in my previous video, I did a logistic regression model, and I did a linear regression model, and when I did the linear regression model, we got the regression, and the continuous variable that came out was the probability that the customer will churn. Well, what we're going to do in this particular piece of code is we're going to use the logistic regression model. And then when you use the logistic regression model, you also are able to get the probability that the customer will churn from the logistic regression model. And that's what we're doing in this video. And so I had to do this all by myself because I'm working by myself and I don't have anybody to help me. So I'm just doing it on my own. And so I figured this out on my own. And I'm sure somebody who has more experience and skill than I do may very well have known the answer to this question. But because I was working on my own, I had to sort of figure it out on my own. One thing that I will do, though, is I'm going to give you the link to the Jupyter notebook in the description box down below so you can go over the code with me. Now, this particular piece of code, I scored 80% when I submitted my work to Kaggle, and it is less than my score when I used sklearn's random forest. But I just wanted to get a Jack's code in here because there's not a lot of code in Jack's, and so I want to build up a encyclopedia of Jack's code that people can use and refer to if they want to use Jack's. So the first thing that we do after we open our Jupyter notebook, and this Jupyter notebook is Play 4.1 Jack's log reg. That indicates that we're using the Jack's library and we're using the logistic regression model in the Jack's library. So the first thing we're going to do is we're going to develop the problem statement. The problem statement is identify the probability that a customer will churn. After we have developed our problem statement, then what we're going to do is we're going to import the libraries that we're going to use. So we're going to import within the program. So we're going to import NumPy as NP, which creates NumPy arrays and performs numerical computations. We're going to import Pandas as PD, which creates data frames and processes the data. We're going to import Jax, which is going to create the model. We're going to import OS, which is going to go into the operating system and obtain the files used in the program. We're going to import sklearn, which is going to provide machine learning functionality and give you the functions for the various machine learning things that you would like to do. We're going to import matplotlib.pyplot as PLT, which visualizes the data, and we're going to import Seaborn as SNS, which visualizes the data statistically. So after we have imported our libraries, what we're going to do is we're going to load the data set using the OS library, and then what we do is we go into the operating system and we retrieve the files that we're going to need. We've got 3 files, being 3 CSV files, being train, test, and sample submission. Now what we're going to do is we're going to use pandas to take the 3 CSV files and we're going to convert them to data frames, being train, test, and submission. So this is your train file. It has 14 columns of data, with the last column being your target, and it's called exited. So we've got the test file, which is similar to the train file, with the exception that it does not have a final column of data called exited, because that's what we're going to make predictions on. And then we're going to have the submission file, which is what Kaggle wants to see when you submit your work to them for scoring. What we're going to do now is we're going to drop the ID, surname, and customer ID from the train and the test data frames. The reason why is because Pandas automatically indexes every row of data, and so you don't really need these rows of data, so we just drop them. We're going to check for unique values in the train data frame, and you can see importantly the unique values that we want to see are for geography and gender. So for geography, you've got France, Spain, and Germany, and for gender, you have male and female. So we're going to check the unique values in test, and again, specifically, we want geography and gender, and I'm very happy to say that the unique values in geography and gender are the same that are in the train file, which is good because that doesn't always happen. Now what we're going to do is we're going to analyze the target, and the target is the exited column of train, and we're going to use Seaborn to do that. And you can see when we use Seaborn to create a histogram, you can see that you have a lot more zeros than ones, so this indicates there is a class imbalance. We're going to do a histogram of geography, so you can see that there are more people in France than there are Spain and Germany. And then we're going to do a histogram of gender, and you can see that there's more males than females. And then we're going to do a box plot of tenure, and you can see that the main body of tenure is very close to being the same for all 10 values, but each value also has outliers. Now what we're going to do is we're going to encode the columns, and so we only have 2 columns of data that needed to be encoded. So I just created a dictionary called dic_df, and we've had France is 2, Germany is 3, Spain is 4, female is 0, male is 1. And then for the train and the test data frames, I replaced all of those values in the data frame, in the dictionary. So now you can see that we have, rather than gender being male and female, and rather than geography being France, Germany, and Spain, you have numbers for those allocations. So now what we're going to do after we have encoded the object columns, we're going to define the X and the Y variables So your Y variable is your target variable, and you're going to pop the exited column out of train. And your X variable is your independent variable, and so it's going to be the remainder of the train file after you have popped exited out of it. And then X test is going to be test. And so your Y variable is dependent and your X variable is independent. So the box plot, we're going to create a box plot. And you can see that when we create the box plot, none of the columns of data are highly correlated, so that's a positive. So that means that you don't have to remove any highly correlated columns of data. Now what we're going to do is we're going to standardize the train and the test files. It's important to do this because I know that I have read in the past that you do not need to standardize or normalize logistic regression, but I tried to run this program without standardization, and it just simply didn't work. So in this instance anyway, I had to standardize the X and the X test variables. So when you read the documentation for logistic regression, they'll say that you don't need to standardize, but in this instance, you did have to standardize it. So the best thing to do when dealing with logistic regression is run the model up without standardization and see what you get, and then run the model up with standardization and see what you get, and select the one that has the best score. So after we standardize the data, what we're going to do is we're going to take the X and our Y variables and we're going to convert them to JAX arrays. And you have to convert them to JAX arrays because the model will not work. It will not train the data and make predictions on the data if you do not convert your X and your Y variables to JAX arrays. And now what we're going to do is we're going to use train test split from sklearn to split the X and the Y variable into training and validation sets. After we split it into training and validation sets, what we're going to do is we're going to define our model, and our model is written in JAX. So we're going to define our key equals jax.random.prng key 42. And after we've done that, we're going to add a bias term to the features, and we're going to do that with xtrain, xval, xtest. And then after we've added the bias term to the features, we're going to define the sigmoid function. So the sigmoid function gives you the probability. And probability equals 1 over 1 plus jmp.exp negative x. And then we're going to return the probability. And after we've defined the sigmoid function, then what we want to do is we want to initialize the weights by defining the variable numFeatures, which is the number of columns in xtrain. And then we're going to define the weights by jax.random.normal brackets key, numFeatures. And then after we do that, we're going to define the hyperparameters. So we set a learning rate of 0.1, and you have number of epochs as 1,000. And I suppose we could have more epochs if we wanted more epochs, and it might possibly even improve our accuracy. And I suppose we could also change the learning rate and see what we get when we change the learning rate. So these are things that you can do hyperparameter tuning to try to improve the accuracy of your model. And then after that, we're going to carry out our training mode. And it's going to iterate through each epoch in the maximum number number of epochs. So in this instance, we've got 1,000 epochs, so it's going to iterate 1,000 times. If you wanted 10,000 epochs, which may have been more appropriate, it could iterate 10,000 times. And then we're going to define the function accuracy, which what that is going to do is that's going to help you determine the accuracy of the model. But in this particular problem, what we want to do is we want to find the probability. We're not looking for whether it's a 1 or a 0. We want the probability that it's going to be a 1. So we're going to make predictions on the validation set. Val logits equals JNP dot dot x val weights, and then val probs, that's your probability, equals sigmoid val logits, and val predicted labels equals val probs greater than 0.5 dot s type ends. So we printed off the val logits, then we printed off the val probs, and we printed off the predicted labels. So now what we're going to do is we're going to calculate the probability by making each value within the probability to be a value between 0 and 1, because that's what you want to see. So we're going to normalize the values. And so this is how we normalize the values with min prob equals val probs dot min, max prob equals val probs dot max, val predict proba equals val probs minus min prob over max prob minus min prob. And that gives you a value between 0 and 1, which is what Kaggle wants to see. So we're using Seaborn to make a diagram of this so that we can look at it, and you can see we've got all the values between 0 and 1, which is what the model wants to see. We're going to get our accuracy. We had an accuracy of 82%. Now what we're going to do is we're going to predict on the test set, and so we're going to use exactly the same methodology on the test set that we used on the validation set. So we're going to find the test logics equals JNP dot dot x text comma weights, test probs, which is your probability, equals sigmoid test logics, and then predicted labels equals test probs greater than 0.5 dot as type int. And so you can see we've got our probabilities and our labels, but this probability that we are looking for. And then so we're going to normalize the probability exactly the same way that we did it on the validation set. And so we will come up with a predicted norm letting you know that it's normalized, and all the values are going to be between 0 and 1. So we're going to look at this on Seaborn, and you can see on Seaborn that all of our values are between 0 and 1, which is pretty accurate considering the fact that when we analyzed the target, you had a class imbalance and you had significantly more zeros than you did 1. So now what we're going to do is we're going to prepare our submission. So we're going to take the prediction norm and we're going to place it in the exited column of the submission. Then we're going to convert submission to a CSV file. And it's this CSV file that we are going to submit to Kaggle. And when I submitted it to Kaggle, I got approximately 80%, which is about 7 points lower than I achieved when I was using Random Forest Predict Proba. But I just wanted to show you how you get the probability from Jax's logistic regression model. So I'm going to go ahead and conclude this video because I've set out to do, which was tell you how to get the predict prober model. So I would like to thank all of my subscribers for supporting my channel. If you like my video, please like, subscribe, and share. And I look forward to communicating with you in the next video.